All right, so it's my job then as last speaker to wake you up again and be entertaining so that you leave with a good feeling for the conference, so I'll do my best. So I'm going to talk about the specification of ixml, Invisible XML. For those of you who don't know what it is, let me just briefly describe it. So it's a method for turning non-XML documents into XML, or at least being able to treat them as if they were XML. So what you do is you write documents, or you've got documents and data in other formats apart from XML. You can process them as XML, and that means that you can import loads of other sorts of documents into the XML environment. So that, in other words, almost everything can be treated as XML. It works by you providing, or there being provided, a format of the data or the document as a context-free grammar. The document is then parsed using that grammar, and then, of course, you get a parse tree out of it, which gets serialized as XML. The grammar has small extra additions that allow you to control that serialization, so you get something that's not too enormous out of it. So just to give you a necessarily small example, this is the definition of the email type in Xforms 2.0, which I've also had to break up into lines just to make it a bit more readable. So if we represent this in ixml, it looks something like this. So it says that email is a user followed by an @ sign followed by a host. And a user, now this is one of the extensions we've added to the grammar, is a number of atoms, one or more atoms, separated by a full stop. So as well as the normal regular expression style pluses and stars after something, saying 1 or more or 0 or more, you can also add something after the plus or star, which says that those things are separated. Now, it doesn't give you any extra power, but it makes grammars very much easier to write. It's much more expressible. So a user is a number of atoms separated by points. An atom is just a number of characters, and so on and so on. So if I take this description of an email and apply it to this example email, and then express express the result then as XML, then it looks like this. So we've already got something quite reasonably structured out of it. I should say that the rule for letGit, letter or digit, has got a minus in front of it, so that you at least get something reasonable with words. Otherwise, you get letGit around every single character. So that's one of the first things that shows you how to serialize. It can say, don't serialize this as an element. We're just interested in the content of this thing. So going back to that slide. So here's then the parse tree that we've got out in XML. Now, the word part of a domain is not semantically interesting. So if we change the rule for word so that we put a minus in front of it, so we say we don't want to see that as an element, then we get something like this. So it's already looking much better. Maybe we're not interested in atom or domain either, so we put minuses in front of those, and then we get something that looks like this. And finally, if we'd rather have the user and host as attributes rather than elements, then we put an @ in front of them, and then we get something that looks like this. And finally, if we want to get rid of that spurious @ as it were, then we just put a minus in front of the @ in the rule for email, and then we get the shortest version. So what I've shown here in this very quick example is that you've got quite a lot of control over how you can serialize the result, and it's very useful for turning stuff that's not XML into XML that you can then use. So at the XML summer school in Oxford this summer, somebody who'd been to one of my talks on Invisible XML said, well, is there a specification for it yet? And I had to say, no, there isn't. But that meant that that very afternoon, I sat down and started writing one. So this is really about what's in the specification now, and also to tempt you to go and look at the specification and give me comments as necessary. So I'm going to sort of just give a top-level view of the specification of ixml, and then talk about future possibilities. So the format that's used for grammars is called 1VWG, which is a one-level VW grammar, and VW is the name of a Dutchman von Wijngaarden, which I don't expect you to have to reproduce. So that's why we just use the initials. It was designed in the 60s. It comes from Amsterdam, actually. It comes from the institute where I work. So a 1VWG is a series of rules. A rule consists of a name, a colon, and one or more alternatives. And an alternative consists of 0 or more terms separated by commas. So expressing that in ixml, it looks like this. So you can see ixml is rule plus, and alternatives is alternative plus a semicolon, which means it's a number of alternatives separated by semicolons. A term is a factor or an optional factor or a repeated factor, so it's just an optional factor is with a question mark after it, and you've already seen the repeated versions. And a factor is either a terminal or a non-terminal, or a bracketed list of alternatives again. Terminals are the elements that match up with symbols or with characters in the input. So we use Unicode characters for that. And there are two forms for terminals, either literal strings or character sets. So literal strings are the simplest. You can enclose them with single or double quotes, and if you want to include the delimiting string quote in the string, then you just double it. There is a possibility of encoding characters that don't necessarily have a representation or are ambiguous. So for instance, #A0 is the non-breaking space. You don't put that in the string, it's just a character by itself, but that's not a limitation, that doesn't limit expressiveness, because a rule like this is just the 7 characters involved. Character sets say, well, match any one character from this set of characters, so we've already seen A to Z, and 0 to 9. The elements of a character set can be a literal string, in which case it can be any one of those characters in that literal string, a range like that, or a character class. Now, what's a character class? These are defined within Unicode. Unicode has 30 character classes, such as lowercase letter, uppercase letter, and so on. And they're all encoded with 2-letter abbreviations. So that's really useful because you then don't have to decide yourself what is a lowercase letter. Saves you having to define those classes. And I think another nice thing is that it makes it easier to make your formats international, because you don't have to know what an uppercase letter is, or what a letter is even, in the enormous Unicode character set. You can just say, give me, accept here a lowercase letter, and Unicode will do the work for you, as it were. One other thing that you can do is exclusions, which says any character that's not in this set. So for instance, if you wanted to define a comment as a bunch of characters enclosed with curly braces, you can do it this way, and you say that in the middle is 0 or more C characters, and a C character is anything that isn't a closed brace. So again, absolutely essential for a lot of things that I've had to define. Now, a non-terminal, so those were all the terminals. A non-terminal is just a name, referring to the rule of that name. Now, the problem is, what's in a name? And so let me ask you this about XML. Is this a valid element in XML? Does anybody think this is valid? That's right. The answer is it depends which mu it is, because there are 2 mus in Unicode. And so if it's B5, it's not allowed as an element name, and if it's 3BC, it is allowed. This is the rule that defines name characters in XML, and I would claim that this is rather opaque. I went round a number of friends and colleagues asking them if they could showing them several element names and saying, do you think this can be an XML name? And quite frankly, they weren't very clear themselves. So what I did was I compared what XML does allow with the Unicode 30 character classes. I don't expect you to look at this, but it's in the paper so you can see what character classes there are. And I did my best to match them up. There's not an exact match, but there's a very close match. So that a name in IXML, we just use the character classes, and so the name start character are all the letter characters, and a continuation is either the name start plus digit number characters and the join, the connecting characters. This means there's a slight difference between what's in IXML and what's in XML. For instance, the underscore A and underscore O letters are counted as letters in Unicode, but not in XML. And Unicode, for instance, classes both of the mu characters as a letter, so that they're both allowed in IXML. So in other words, it's the responsibility of the IXML author to ensure that names that are going to be serialized, and they don't have to all be serialized, adhere to the XML rules. But there are, as I say, there aren't big differences. But it means that it's less opaque what's actually allowed. Of course, spaces and comments are allowed between symbols, and this is the definition of what a space is. It's either a white space or a comment. And so here for white space, you can see one of the Unicode character classes, ZS, which is what all the characters that are classed as white space in Unicode are allowed as a white space character, to which I've added the XML tab, line feed, and carriage return, which are not classified as white space in Unicode, but classified as control characters. This definition says that comments can be nested, which means that you can comment out a bit of an IXML grammar and it will still work. So that's the definition of the grammar. So now just to talk about the process. So we don't specify which parse algorithm is to be used, but we do put constraints on the parsing algorithm that's used. It must be able to accept all context-free grammars, so there's no limitations like LL1 or LR1 or whatever. And it must be able to produce at least one parse of any document that matches the grammar. Those are the two restrictions. So, as I already said, by default, the parse tree is serialized as XML elements without leaving anything. So if you don't add anything more to the grammar, then you just get the parse of the document in its entirety as elements. Non-terminal nodes are output as XML elements, and terminals are just output straight. So I'm not quite sure if I need to give another example, but here's a very small example of an expression that just allows a series of operands separated by operators, no operator precedence. And if I parse p times 10, then I will get this XML document out where each letter is a separate element. So to control the serialization, there are three possible things you could do. The default, which is, so you hardly ever need the hat symbol because that's the default, but that says the rule should be serialized as an element. At, which says that the rule should be serialized as an attribute, in which case all the terminal elements of the parse get collected together as the value of the attribute. And finally, a minus, which for terminals means it doesn't get serialized at all, and for non-terminals means that it gets serialized in the same way as an element, except without the element name around it. So you just serialize the children, in other words. So this only gives you one unusual case, and that is if you specify a rule that isn't serialized as an element, and it has children that are serialized as attributes. And what that means is that those attributes have to be attached to a higher element in the parse tree than at the level that it's specified. So just to give an example, with using the same expression grammar that I just used, here I've said that so it says an operand is either an identifier or a number, and I've said an identifier is not serialized, but it has a name attribute. And so that means the name attribute will be pushed up to the operand level. So pi times 10 now gives you this operand name equals pi. That's the only odd thing that happens, or maybe an initially unexpected thing that happens with serialization. A grammar might be ambiguous. You might be able to get more than one different parse out of one document according to the grammar. And so what we say is that in the case of ambiguous parses, one of the parses is chosen. We don't specify which one, and that gets serialized. But on the root element, an attribute gets added to say that it was ambiguous. Now, the thing is, as you might have seen, ixml is defined in ixml, which means that we can parse the grammar with itself and then serialize to XML. So in other words, get an XML version of the grammar of itself. So then that meant we had to design what the XML parse serialization should look like. And so what we decided was to put all semantic terminal symbols in attributes and just leave the rest in the elements, so that attributes are the place where all the semantic information goes. So this is just one example of, or a part of an example of the serialization. So that's the full rule for rule. So that's the rule that defines itself. And this is the serialization that we get out, so that you can see the rule has got a name, and it's got a single alternative, and that includes bracketed sub-alternatives. You don't have to look at the details here. It's in the paper if you're interested in more of it. But in other words, this is what you get out at the back end. Now, the thing is, this is the process of using ixml, that you get a document, and square things here are text documents, as it were. Triangular things are the XML versions of them. So you get a document, you pass it through ixml, and you get an XML version out of it. And you parameterize the ixml parser with the grammar of the document that you're converting. So it's the XML version of the grammar that you're using, and not the text version of the grammar. So where do we get that XML version of the document? Well, of course, by doing that, we take the text version of the grammar for the document. We give the parser the XML version of the grammar for ixml. Sorry. And then we produce the grammar for the document in ixml. And of course, then we've got a last step here. Where do we get that XML version of the grammar for ixml? Well, by bootstrapping it one level through itself. And of course, these two things are the same document, so it is a bootstrap. You either have to, in the very first cycle, hardwire that in or write it by hand. So when I bootstrapped it, I just made a first version that had the grammar hardwired, and now I can take the XML version. Since it's the XML version of the grammar that gets accepted, it means we don't really care about the external version of the grammar, the text version of the grammar. So it means that if you prefer your grammars in this style, then you could write an ixml grammar for this style, and as long as the serialization is the same, it will work just fine. So you're not hardwired, it's not hardwired into using the ixml grammar as I've just described it. That's as it were, the base grammar, but you can define as many grammars for ixml as you like, as long as the serialization is the same. So we have a pilot implementation, which I've used for producing all the examples in this talk and in the paper. And my next step is really to turn that into a full-strength implementation in some language that other people want, and people agitate for different languages, and I haven't yet decided exactly which one to do, but I'm working on it. So if you look at an ixml grammar of a document, you can sort of see it as a type of schema for an XML format. And so what we want to do in the next steps is to look at the possibilities of using ixml to define XML formats. For instance, this is the XSL description of the bind element in Xforms 1.1 in the spec. This says that bind is a complex type. It can have a number of children, which is 0 or more bind elements as children, and then it's got a whole bunch of attributes, an attribute group, and then a number of individual attributes. Well, I can just represent this straight away in ixml, and well, it's actually shorter, and I would claim actually easier to read into the bargain as well. So this is the sort of thing I want to look at, but the main hurdle at the moment is that in a grammar, a rule must, if a rule that's got a given name has to always just have one content model, as it were. Whereas in XML, an attribute and a child with the same name can have different content models. So I have to think about the best way of dealing with that. As another example, the input element in forms, in Xforms, looks like this. And I can turn it very simply into this, which is I claim more readable. So, and the nice thing is that you could even define a compact version of XML formats. So, for instance, if I was going to make a compact version of Xforms, then I only have to add a couple of words to that definition, and all of a sudden I've got a compact version, a non-XML version of Xforms, which I just put through ixml, and I get the XML version of Xforms out at the other end without having to have used any angle brackets at all. So my conclusion is that a host of new XML documents are now open to the XML pipeline, and that's I think, the major advantage of ixml. You could also, I wasn't sure whether to say this, but you could also say that it mitigates the loss of SGML minimization in a certain way, because you can transform documents that aren't XML into proper XML. By defining ixml in itself, it means it's its first large application. So the future work will be looking into defining, creating formats in a compact version and an equivalent XML version in parallel. And I do ask you, if you're interested, to look at the specification, which you can find on my homepage. And if you can't find my homepage, you're in the wrong job. That's the end of my talk. Before you clap, though, I just want to give an advert. To also, while you're on my homepage, to have a look at the video, The 100-Year Web, which I gave, a talk I gave at Balasage, and if it convinces you to join the new organization that we're trying to create, markupdeclaration.org, which is to support the future development of XML and other declarative formats. The end.
Impressive. Any question? Okay. Abel, again.
Go.
Thanks very much. Very good, Steve. Two questions. One is, I suspect it's fairly easy to preserve the white space if you wanted to from the input document.
It all gets preserved. In fact, it's harder to not preserve it.
Right, okay. And the second thing is then going in the reverse direction is pretty trivial. If you haven't used attributes, you just push out all the text, and that's the answer.
If you don't use attributes, that's right. Then you can just output the document, and you get the original one as it was. If you start getting rid of stuff, then it's harder to reproduce the original document, as it were. And that I should have mentioned that in future work as well. I mentioned it in an earlier paper. I believe that you can round trip even in many cases where you've dropped stuff out of the document. by parsing the parse tree. I haven't tried it yet, but I believe it can be done, and that's one of my future bits of work, to round trip, even if you drop stuff.
When you say drop stuff, I mean, if you drop structure, that doesn't matter, but if you drop actual content...
Well, it does matter in the sense, let me give you an example, that you might have expressions where you can have two different sorts of brackets. And if you drop the brackets, you can't reproduce the original document anymore. So it does have some feedback. Who's got it? Oh, yeah. All right.
Without extra embellishments, can a parser produced by this technology produce decent diagnostics on syntax errors?
Well, decent. I haven't put a lot of work into this, but I produce sufficiently good diagnostics that I can work out what's gone wrong.
I'm just thinking of the classic problem, you know, of something that says this is not a program.
No, it's much better than that. It says at this point I was expecting one of these following characters. I use the early parser, which tries absolutely everything that's possible at that point. I mean, which is a requirement of the parser of ixml. And if nothing matches, then it says, well, at this point is where I had to give up, and it's not as bad as no, this didn't parse. You really do get some diagnostics, but I'm sure that if you put more work into it than I have now, that you could produce better diagnostics even than that. But it's sufficient. It's sufficient as it is, and but it could be better. Abel.
Hi. I was just wondering about, it seems like XML is a little bit more permissive than XML when it comes to the naming schemes, white space acceptance, and some other things I saw on your slides. I assume that's deliberate, but doesn't that lead to some issues, compatibility issues, translation issues, parsing issues?
The issues are, amongst other things, well, so XML can parse absolutely anything, but there are some characters in absolutely everything that can't be represented in XML in any way whatsoever. Yes. I mean, there are certain characters completely excluded. It is your responsibility to make sure they don't get passed through. So you can do that with a minus sign, say don't pass this through, but you will lose it.
Yes. Okay.
Yeah, you will lose it.
Okay. Thanks.
Thank you. Stephen.
Where am I looking? Wave. Oh, there. Right. Hi.
I think you could also call what you have achieved I-tree, invisible trees, because I think the main point is not XML. It is to see the trees in anything. And I think there are very good reasons to base everything on XML. There are two main reasons. One is a very mature information model behind it, which doesn't exist outside of XML, and the other is fantastic tools. But I would find it very important that people understand that it's not about XML, it's about trees. And when you have understood that, look, numbers, why are numbers so powerful? Because we can do amazing things with numbers. And therefore, why are trees so powerful? We can do amazing things with trees. And XML technology has shown the way. And therefore, of course, you had to embrace XML. But I mean, to get the full traction, I think the message would have to get across that in fact, you are like the painter. We've seen in the painting of Magritte, you look at something and you see the tree in it. And there is an enormous, groundbreaking power in that.
I absolutely agree with you. I mean, I think I did toss up about whether just to call it invisible markup language. But the thing about XML, of course, is that it's of all the tree operating languages, it has the most, as you pointed out, it has the best toolchain available. But you're absolutely right. It is about trees, and in another of the papers that I do talk about using other representations for the trees, including JSON, which is possible, although much harder than in XML. So I perfectly agree, but yeah, no, well, I agree. You're right.
Another question? Gerrit.
Yeah, it's more of a comment than a question, and it's only tangentially related to Stephen's impressive presentation. I just want to express my, and I think all others' gratitude towards the organizers of this conference.
Yeah.
Thank you. Okay, so it was the last question, so I will ask my fellows to join me. Petra, Katja, Jirka, everything is in A.